All right, the method essentially uses an approximation of trapezoids underneath the curve to get an approximation of the area under the curve between the curve and the x-axis from x equals a to x equals b. So graphically, what you'd be seeing would be something like this in your curve. So let's just take a couple sample. Say between these 2 points, if you drew a line coming in here like that, you'd have a trapezoid. The height is down here. This is h, and that is our delta x sub I. That's the same distance. And on this side, we have f of x sub I, and over here, f of x sub I minus 1. So put those together, and you get this formula here. And that gives you so that's a little better than, say, using a rectangle, which would come across like this, or even like this, which would have too much area. So we're thinking the trapezoidal rule is going to give us a little bit better approximation. And for the money, it does work just as well as the rectangle summation. So we have the trapezoid rule here. This summation actually does expand this way, and that's how we're going to look at it. So a little bit of algebraic manipulation. This sum actually ends up being this thing here. So we're just gonna, all we have to do with them is find those x sub i's, basically, and use the formula to generate them. So for this curve, we're going x squared plus 1, we're going from 0 to 1. So, and we're going to use 4 subintervals. You have to decide that up front. So that means we can do this without a lot of math. If that's 1, this is a half, this is a quarter, this is 3/4. And of course, this is 0. So we have all the things we need. We can get our area, which will be approximately this sum. We have the b minus a over 2n. And then we have the f of x of 0 plus 2 f of x1 plus 2 f of x2, 3 f of x3, and finally f of x of 4. So that's just using our formula from above here. You can see this one right here. Okay, so let's put in our numbers and see what we get. So let's see, this would be 1 over 8. And then we would have f of 0, which is 0 squared over 2 plus 1, plus 2 times 1/4 squared over 2 plus a 1, plus 2 times 1/2 squared over 2 plus a 1, plus 2 times 3/4 squared over 2 plus a 1, and finally plus 1 squared over 2 plus a 1. That's our last term. Okay, so it's really just arithmetic from here. If you have a large value of n, then you might try to enlist your summation features on the calculator to get this done, but we can get this one done by hand. Let's see, let's do this, try to do this systematically. This is a 1, and a 1 over here, so that makes it 2. We got a half there, so we'll take care of that. That's that. Then now in here, let's see, we'll have a 2. If I expand this, multiply out, I'll just have 1 over 16 plus 2. Expanding this. The next term, I'll have 1 over 4 plus a 2. And the next one, I'll have 9 over 16 plus a 2. It takes care of all the terms in there. 1/8. Let's see, we got 1, 2, 3, 4 times 2 is 8. And you have 2, 4, 6, 8. Now we've got 10/16, which is 5/8. Okay, and then you have half and a quarter is 3/4. So that takes care of that. Okay, so we have 1/8. It looks like we've got 8 plus, well, you know what, let's, yeah, well, okay, I'll just keep going with this. 8 plus, 8 times 8, let's say, plus a 5, plus 6 over 8, which is, let's see, we'll say 1 over 64 times 64, and 11 is 75. So it's 75 over 64. 64 plus 11 is 75. There you go. Okay, now it also says compared to the actual value found using the fundamental theorem. So we're going to have to come down in here. So let's use the margin here. So we know how to do this one. 0 to 1, x squared plus over 2 plus a 1. And that would become x to the third over 6 plus an x evaluated from 0 to 1. That becomes 1, 6 plus 1, which is 6, 7 over 6. Okay, so how close are the two? Well, that first one there. So over here, this is about, well, exactly 1.171875. And this one is 1.166, repeating. So pretty close to the actual. I guess it would depend on, you know, the concavity of the curve has an effect on your accuracy. The more linear the curve is, it seems the better the estimate would be, since there being less loss or extra involved when you put those like up in here. If this is more linear for the same number of trapezoids, if this is more linear, then you'll have a better estimate. If it's much more curved between each one, you will have an excess, or if it's concave down, you'll have a loss of the area. So, of course, increasing n removes those gaps, but for the same n, a linear curve would lend itself better to trapezoidal rule. Okay,